Hello, everyone. This is Chao from Peking University. Today, I'm very glad to share our work, Jolteon, unleashing the promise of serverless for serverless workflows. This is a joint work with Zili and Zhang from Peking University. Serverless computing is becoming an exciting cloud computing paradigm. Many cloud providers and open source communities are providing serverless platforms, such as AWS Lambda and Azure Functions and so on. At the core of serverless computing is fine-grained resource elasticity and fine-grained billing. The resource elasticity enables users to easily scale up and down, and the billing policy ensures the charges are only incurred for active running with 1 megabyte memory granularity and 1 millisecond time granularity, which makes serverless a very cost-effective choice. So the benefits make serverless attractive to deploy cloud applications. As we can see, many cloud services like AWS Step Functions and Azure Logic Apps and Google Workflows have supported serverless workflow as a main product. Typically, these cloud applications have a job execution DAG, which is composed of multiple stages, and each stage composed of multiple parallel tasks. Users deploy the tasks as a pool of serverless functions with 2 performance goals. First, we want the job to complete as fast as possible, which corresponds to workflow execution latency. And second, we also want the job to execute with the lowest cost. On major serverless platforms, the cost of a function is defined as the product of its execution time and memory usage. And this paradigm introduces a new problem for serverless users. As we know, the number of parallel functions or the degree of parallelism and the function size, including the number of vCPUs and the memory capacity, composes the resource configuration space of one stage in the workflow. And the fine-grained resource management of serverless computing enables us to adjust the parallelism configuration and function size of each stage. For example, a stage with more resources introduces a lower latency but may higher cost, while a stage with less resources introduces a higher latency but lower cost. As a result, here we are wondering, can we decide the resource configuration automatically for serverless workflows and satisfy their application level requirements? To answer this question, we first needed to build an accurate performance model to capture the relationship between resource configuration and the workflow latency and cost. Typically, the cost is, as mentioned, usually defined as proportional to execution time in serverless computing. So we only profile the execution time here. Several works leverage a whitebox model to deterministically predict the function execution time with analytical formulas. For example, Ditto divides function execution into several fine-grained steps, including data transmission and computation. And it builds individual equations for each step and based on the computation or transmission logic. The model recognizes that the transmission time remains constant when the number of vCPUs exceeds certain threshold, given that it saturates the network bandwidth. However, the analytical equations neglect the intrinsic performance variability in serverless computing. When given a fixed resource configuration, the corresponding execution time is a distribution rather than a fixed value. Some other work collects function execution information and traces as sampling data, and then fits a black box model like linear interpolation or Bayesian optimization to cover the function execution process. The model indeed outputs a distribution for a given resource configuration, but it overlooks the underlying serverless computing characteristics. Now imagine, given an ideal performance model, the next step is to solve the optimization problem to find the optimal resource configuration given a latency budget or given a cost budget. First, let's consider the example of one stage. For one stage, the potential configuration space is derived from varying function sizes combined with different degrees of parallelism. Given that there is only one stage, the configuration space here remains relatively small. With a perfect performance model, we can just enumerate every possible configuration to identify the optimal one. But when we dive into complex serverless workflows, things get a lot difficult. In a serverless workflow, the first issue arises when the number of stages increases, leading to exponential complexity within the configuration space. In such case, enumerating all possible configurations becomes impractical. And as we discussed above, the performance model should be aware of the execution time distribution, but for a complex workflow where one stage may have multiple downstream stages or upstream stages, we have to combine different distributions in addition and in parallel. This adds more efforts in performance model to calculate the final distribution of the entire workflow and makes enumeration more impractical. Existing works like NSDI 2022, Orion, and SECOM 2023 Ditto employ heuristic method to solve the optimization problem. They only achieve suboptimal results within their limited search space. And this slide presents an overview of the challenges and how Jolteon prepares to solve the problem. For challenge 1, we develop a stochastic performance model that captures the benefits of both analytical and distribution-aware models. And for challenge 2, we first formulate the optimization problem and then propose a stochastic optimization algorithm with convex property, which gives an optimal result with a reasonable solving time. We first focus on the execution time of one function, which we divide into initialization, data transmission, and computation. In initialization, the first step is the network delay and the front door execution time. Front door execution time contains security check and scheduling in the platform. This part is inherently variable, influenced by the network status and the platform status. We have gathered data of the time from AWS Lambda, as shown in this figure. Evidently, this time is not stable. We model it as a random variable D. The second is image transmission time and container loading time if the execution is cold start. The time of this step is influenced by the image caching system and image size. It is also unstable. When the execution is warm start, the time is nearly 0. So we model this step as random variable G. G is equal to 0 when it is warm start. As for transmission, one function execution may include data downloading and uploading. We model data downloading as an example. The size of input data for a stage is a random variable which denoted as S, and the stage comprises D parallel function instances. Let the available network bandwidth be B, and the number of vCPUs of a function instance be V, respectively. Apparently, the data size of one function is S divides D, and the data size divides the network bandwidth plus one API invocation time is the final data transmission time. As for bandwidth, it is proportional to the number of vCPU, V. However, the bandwidth reaches to a saturation point when V is sufficiently large. The saturation point here represented as uppercase B. And this equation and the corresponding curve is shown in the figure. Notably, all variables in uppercases letters represent random variables. And as for computation, the function logics are diverse. Some logics process data in size of S divides D with linear complexity. Some may process data with logarithmic complexity. We focus on two typical function logics, those with polynomial complexity and logarithmic complexity, and propose the corresponding equation to approximate the computation time. S divides D plus V, D times V, is the data size processed by one vCPU. And AI and BI here are positive coefficients and are random variables. D is the number of parallel functions in one stage, and V is the number of vCPUs for one function. If the function cannot utilize multiprocessing or multi-threading, V is constrained in 0 to 1. This formula is not applicable to function logic with other complexities like exponential complexity. However, since the feasible domain of V and D is discrete and finite, other complexities can be approximated by the above polynomial complexity through Lagrange interpolation. The aforementioned performance model pertains to an individual function. For one stage, we have to consider the D parallel function instances. The latency of the entire stage is the maximum latency of all parallel functions. And the cost of one stage is simply the sum of all parallel function costs. As for the workflow, it is composed of in parallel stages and in series stages. For in parallel stages, the entire time is the maximum of the stage time. And for in series stages, the entire time is the addition of the time. In conclusion, our stochastic performance model are analytical formulas with random variables. It not only captures the inherent variability, but also uses analytical formulas to capture the system characteristics in serverless computing. It can accurately and quickly predict the performance bound. Then we need to formulate the optimization problem before we solve it. Bold letters DV represent the vectors of the workflow resource configuration, contains multiple stages of parallelism configuration and vCPU configuration. We use optimization on cost within a latency budget as an example. This objective function is the cost of the entire workflow. It is calculated by the sum of all stage costs. And the constraint here is to guarantee the latency bound epsilon with confidence level delta. In Jolteon, we set the confidence level as 99.9%. The objective function and the constraint function both contains random variables, which makes it a chance constraint optimization problem. It cannot be directly solved. One way to solve the problem is to transform the chance constraint problem, chance constraints, into a set of deterministic constraints by sampling the random variables. As for objective function, we can use expectation values to replace the random variables. The new sample constraints is a deterministic function, but it introduces a new question. How many samples should we have? As shown in this demonstration, more sampling yields to a more accurate fitting. And, but a large sample size introduces high sampling overhead and intricate problem formulation with very large solving time. To solve this problem, we leverage sample approximation theory to calculate the minimal sample size as shown here. Percentile refers to the percentile for the target bound, such as 95% latency bound. And D is the definition domain of vector D and V. The detailed proof can be found in the paper appendix. This lower bound of the sample size allows us to guarantee the performance bound with confidence level delta while reducing the sampling overhead and solving time. The chance constraint optimization problem, the algorithm, is transformed into a deterministic optimization algorithm. The paper further proves the convexity of the deterministic optimization problem. Thus, we first apply a gradient descent algorithm to find the optimal result. And the convexity guarantees that the local extremum is globally optimal. But such result may not be feasible since AWS Lambda function has restrictions on the function size. So we then apply a probe process by iteratively examining the feasible points surrounding this extremum. Finally, the optimal result and the feasible configuration comes out. We implement a system prototype with 3,000 lines of code in Python. The system workflow is shown here. Before we run Jolteon, it will collect the history, execution data, or execute the workflow a couple of times to build the profiler. And when user defines the performance bound, Jolteon calculates the optimal configuration and deploy the workflow to serverless platform for subsequent execution. We evaluate Jolteon on AWS Lambda. The scheduling part is deployed on one centralized node, and the function computing is based on AWS Lambda, and the data transmission is through AWS 3. As for the workload, we use 3 representative serverless applications: ML pipeline, video analytics, and TPCDS query. These 3 work workflows of these applications, of the three applications, have different characteristics in terms of the number of stages and the data dependencies and I/O and computer demands. We first compare Jolteon to all baseline systems. Orion uses heuristic search to adjust the function sizes while using deterministic numbers of parallel functions. And Ditto uses an algorithm to minimize either latency or cost, adjusting the parallel function numbers. And Keras uses the degree of parallelism, which is proportional to the input data size of each stage. Thus, three baselines only achieve suboptimal results due to their limited search space. Jolteon is able to find a Pareto optimal latency cost curve. And to evaluate the latency guarantee of Jolteon, we set different latency bounds and measure the actual latency. This figure shows the actual 95% latency and the ideal latency for the three workflows. The measured actual 95% latency is consistently less than and close to the ideal line, which demonstrates the capability of Jolteon to provide a latency guarantee. And the cost guarantee is similar. When the cost bound is relatively loose, the actual cost is nearly unchanged. This is because the optimization objective is latency here on the cost bound, and increasing resources does not further reduce latency. In such cases, Jolteon avoids unnecessary allocation of resources. And for more evaluation results, please refer to our paper. Finally, I want to conclude the talk. We present Jolteon, a serverless workflow orchestrator that facilitates automatic resource configuration to satisfy application-level requirements for serverless workflows. Jolteon uses the stochastic performance model to form an optimization problem which minimizes the cost on the latency or minimizes the latency on the cost bound. And Jolteon outperforms Orion by up to 2.3 times on cost and 2.1 times on latency. And compared to Ditto, Jolteon reduced the cost by 1.9 times or latency by 3.3 times with less than 11% reduction on the other metric. And this is the end of my talk. Thank you. I'm ready for the questions.
Thank you.